This is Kat Zien.
Well done.
Close enough?
Yes.
All right. And her interesting fact is a couple weeks ago, she rode a bicycle from Copenhagen to Berlin for charity, which is over 150 kilometers in 3 days. So
That's a lot for Americans, by the way. Google it.
yeah, it's like 100 miles.
Yeah, no, but most
That
Americans.
was 450.
450?
400.
450 miles.
No, 450
kilometers.
Oh, kilometers. Oh,
150
okay.
kilometers a day.
No, overall 3 days. So it was about 100 miles a day.
100 miles a day. There we go. That's even more impressive somehow. I don't.
That is.
It's like when you said it in miles, I was
and
like, wow, that's
they raised
impressive.
over 75,000 euros for charity.
Wow. Good for you.
And with that,
50 of us. Hello, everyone. Great to be here. Great to be able to speak to you today. So my name is Kat, and I am this weird, unpronounceable Twitter handle, which is actually my Polish name. And I picked it before I moved to the UK about 10 years ago, and then I told everybody to call me Kat, but I'm kind of stuck with that now. So, yeah. As developers, when we start working on a new project, we usually start with planning. So we think about the requirements and the scope, and maybe we have a few planning meetings, we do some designs, we write some documents, and then we start to think about the code itself, and we think about the logic and how it's all going to work. And then we write some code, we write our tests, then we run the tests pass, we're good to go, right? Well, not really. Where is performance in all of this? So this is typical for a lot of developers and a lot of projects. We kind of tend to forget about performance. And you can't really blame people for that, because analyzing performance is hard. And it can seem quite tedious as well. So I'm going to show you today how you can get started with performance optimization. And this kind of comes from my own confusion when I had to do it all at work for the first time, because I had no idea where to start and what tools were there to help me with that and what all those weird stack traces mean and all of that. So let's start with the most obvious question. Why should we care about analyzing performance of our apps? But I'm not going to spend too much time on this, though, because hopefully we all know the answers to that already. In case they are not obvious, how about this? Fast is generally better than slow. Duh, right? Memory efficient is good. Saving money is good, because you might need less servers to run your apps if it's been optimized. Running out of memory in production is bad. And suddenly running out of memory in production is really bad. So that pretty much covers the whys. In terms of when to start looking at performance optimization, we can and should be looking at it pretty much every stage of the software development lifecycle. So when you're writing your app, or when you're asked to take an existing app and analyze its performance, it's a good idea to see how it performs in your local machine. And chances are you will be able to spot some issues on your local machine already. There may obviously be a dedicated load testing phase before you release your software to production. And this is where you have a chance to simulate some real-world traffic to your app, for example, in your staging environment. And when you're doing that, you should try and establish the minimum and the maximum and the average amounts of requests your app can handle, for example, because that will give you a good idea of how scalable your program is. So if there is a big difference between the minimum and the maximum, for example, it might mean that your app will not scale very well if you suddenly get 10 times more traffic. And also knowing those numbers, like your sysads and your DevOps people will love you for that, because then they can provision the right kind of infrastructure to run it on. And then finally, when you're done working on your software, you should still keep an eye on performance in production, even just to have some historical data to compare against when you're making new releases, just to see if the performance is degraded or if you've improved it over time. And we won't be able to tell that without having that historical data. And needless to say that having some real-time monitoring in place allows you to spot any issues quickly or any spikes and then react. So a very common question is what to optimize. My favorite strategy is kind of to start with this question all the time, which is, do I need this or do I need to do this? And this isn't like me being lazy and asking whether I have to do the performance optimization or can I just get on and with something else. This is what you should be asking yourself whenever you look at your code is doing. Because, like, sure thing, you can change something in your code for it to be faster, and make it more efficient, but getting rid of something entirely is the best kind of optimization you can make. So keeping an eye out for any dead code or any operations that you can maybe do once instead of multiple times, those kind of things, like removing those is the best thing you can do. And so I never thought I'd say that, but lazy kind of beats busy when it comes to performance. So take the lazy approach and basically make sure you absolutely need to do everything your app does before you start even optimizing it. And if you do need to do something, then make sure you only do it as few times as possible, or only the amount of times that you need it to do. And this is kind of very easy to forget about. Like, people tend to jump into optimizing straight away, but without taking the step back and actually seeing, do we actually need to do this? And yeah, it's by far the easiest optimization to make, and you don't really need any tools for that. You just need to look at the code. But more seriously, in terms of what to optimize, most of you will have a pretty good idea already. Because generally, optimizing performance means either making things run faster or consume less memory. So you should try and reduce the amount of time it takes to do something in your program by reducing the amount of operations you do, or you should try and reduce the amount of memory you're using. And this is kind of my very unscientific graph, where I kind of wanted to illustrate that goal. So the three aspects we're looking at is the memory, the time, and the code itself. And obviously, you're aiming for using as little memory and short execution times and no redundant or efficient operations. So that's the 0 point on the graph. But in reality, that is kind of a little bit of a unicorn. It's something you can asymptotically try and move towards, but you shouldn't necessarily expect to get there. And this is because optimizing performance often compromises readability of your code, for example, or the simplicity. And that is something to keep in mind. So it's more of a balancing act, and you just have to stop at the right point. It's easy to take an app and start diving into every single function and spend a lot of time going from function to function, but that not really may be feasible for large projects, and it might just easily become overwhelming really quickly. So in reality, you need to focus on the hot paths in your code first. And we'll have a look at that later, how to identify those hot paths. And this will help you stay focused and stay on the right track, and will probably bring you the biggest gains. And because we have all the deadlines and long to-do lists in real life, we kind of often just need to make sure that the app is good enough in production. Like, if your app receives 1,000 requests per second and on average, and you're not expecting it to be 10K requests anytime soon, but you've already optimized your app to handle that much, then maybe that's a good place to stop, and you don't need to optimize anymore. So make your app run as fast as it can, using as little resources as it can, but within reason. So don't necessarily expect to get to the unicorn. And there are certain things that are well known to cause potential performance issues, and which you should always watch out for. So things like memory leaks, it could be unbound variables or stuck or unreachable Go routines, race conditions, which may often lead to deadlocks or live locks, heap allocations, which means more work for your garbage collector, and I'll come back to that later. Inefficiency or redundancy in your code, as I already said, so doing the same thing more than once unnecessarily, and even dead code or unused libraries, where you might be initializing something that never ends up being used. Even things like the size of your code base can affect performance, or at least the compilation time of your program. And there are a whole bunch of known gotchas or general rules that you find online, and performance tips, which can be good guidelines when writing code, such as this list. And this is by no means an exhaustive list. It's just an example that I found on this website. So things like prefer stack over heap allocations, because whatever gets allocated on the heap has to then be collected by the garbage collector, and rather than just being automatically removed from the stack when your function returns. Prefer values over pointers for not big structures, because pointers and interfaces tend to get allocated on the heap. So sometimes a little bit of copying is better than using pointers. Pre-allocate the maps and slices if you know the size beforehand. Don't log if you don't have to. the log package implementation uses a mutex to synchronize access to the file. Like if you have multiple Go routines, they all share the same mutex. So that tends to come up in profiling traces quite a lot. Use buffered.io if you do many sequential reads or writes to reduce the number of system calls to read or write. So basically just buffer it all up and then read or write it once at the end rather than as you go along. And if your app does something with JSON, like encoding, decoding, then consider looking into alternative libraries other than the standard library. So for example, EasyJSON, which is one of the ones that I used before, that claims to provide a fast and easy way to marshal and unmarshal ghost tracks without the use of reflection. And in performance tests, they claim to outperform the standard library by a factor of 2 or 3 times. And remember that every single operation matters in a hotback. So again, that goes back to the lazy rule. And there are, of course, a lot more tips like this. So this is just a small example. And you kind of tend to find them over time as you get more experienced. So that's all well and good, right? We have the theory, but that's good when you know how to analyze performance and arrive at those conclusions. So how do we discover those things? And the how is what most people get stuck on, and myself included. So especially if you're faced with a big project with many, many lines of code that might not even be yours, so you might not know what's going on under the hood, that might just very quickly discourage you and go, you know what, I'm out. So how do you find out what to improve? How do you know how your app is doing? Or is it as efficient as it can be? And how do you gain that visibility? And how do you know what your app can handle? How do you know it's not leaking memory? Will you run out of memory if you get 10 times more traffic? So how do you prove the guesswork? You might already have some ideas, but how do you prove that? And the general answer is, of course, measure. But then how do you measure? And what do you measure? And how often do you measure? And so these are all the questions that I had. And so I thought it might be useful to do like a little practical example of how you actually go about improving performance. And the pun is kind of intended and unavoidable. So let's start with the tools. There are obviously different kinds of tools you can use to analyze performance, and it is kind of important to have the distinction in your mind between what each tool is useful for. So you've got your monitoring tools, and it's good to have those set up. You might already have them set up, so you might already have some performance data to work with. And most of these tools, like the New Relic and Datadog and the Elk Stack, they will give you some graphs, like pretty easy to digest graphs that show you the bigger picture, like the memory usage, or like the CPU, how busy it is, that kind of thing. And so you might be able to tell from those graphs whether there is something or not that you need to worry about. Because if you see a spike in your memory graph, for example, then that has an upward trend, then that might suggest that there is a memory leak somewhere. If you don't have the production data available, then there are tools that can help you simulate the load, like production load. And these are the load testing frameworks. And there's one for every major language under the sun. There's some pretty big ones like JMeter and Gatling and Taurus. But there are also a few smaller ones written in Go and kind of for Go, like Go WRK, which is what I tend to use, or K6 or Pew Pew, and there's probably a bunch of other ones. So that lets you fake some load into your app and gather the profiling data that way. But you might not even sometimes need to go as far as that. You might just write some benchmark tests, which will then execute a bit of code that you tell it to, or the whole app, over and over again, and until you get some stable, meaningful usage results back. So I'll show you an example of that later on. So monitoring and local testing, they only kind of give you a higher level idea of what's going on inside your app. So no matter how great the setup is, it won't really tell you what's going on inside the app. So for that, we need to dig deeper. And so we need a profiler, which will give you some more detailed, more low-level information like stack traces and what's going on in the memory. And then we can use some visualization tools on top of that, which will basically make it easier for us to make sense out of all the data. Which kind of brings us on to the demo time. So I spent ages trying to come up with an example app that we could optimize, but the trouble with like the typical Hello World apps is that they're very simple, and they're simple to reason and optimize, and that's kind of not what the real life is like most of the time. So I've decided to actually use an actual problem we had at work as an example. So, and the upside of that is that this is kind of how most of the performance optimization tasks start, that you ask to analyze something you know very little about, and something that is quite large and complex. So one day our ops team came to us and said, hey, that the memory graph for this app is going up, so what's going on? And this is kind of what they showed us in Kibana. So the first thing we did was ask them like what has changed between now and when the memory graph wasn't going up, because we haven't done any code changes, we haven't done any releases. And they said, well, we turned on a sensu check. And the sensu, like for those of you who don't know it, it's just basically it's a tool that you can use to ping an endpoint in your app, and it will verify the response back and basically alert based on whether the response is what it expects or not. So they turned that on, and they used one of the internal endpoints that the app exposed. So the app was a reverse proxy of sorts, and it exposed an internal endpoint called metrics. And so they decided, because that was the only internal endpoint that we had at the time, that this is good enough to like ping and verify that we get some good results back, and that means that the app is up and running. So this was one of the many checks that they do. It kind of tends to be the more the better, so they don't tend to be super solid. It's just kind of a rough yes or no. And so once they started poking that endpoint every minute, because the sensor checker was running every minute, then we saw the memory graph going up. So because of that, we kind of had a clue of where to start monitoring. We basically just took the code and go, okay, it's somewhere in the metrics endpoint that things seem to be going wrong. And when we so this is the output of the endpoint that it gives you. It just gives you sort of like a blob of JSON with a dump of metrics that we've collected in the reverse proxy. So things like requests received and that kind of thing. So now that we know what the symptoms are, we need to work out the causes. So we need to do some diagnostics before we can actually produce a diagnosis. And to do that, we need to work out what's going on inside that metrics endpoint. So looking at the code itself might not really give you many clues, because it all looks fine. So we need a way to dig a little deeper. And that means we need a profiler. So luckily, Go comes with a profiler built in. It basically needs a server to expose its own endpoint. So if you don't have a server running in your app already, you can just open up the standard HTTP server. You just include the line at the top, and we're good to go. So it gives us web endpoints that we can open up in the browser /debug/pprof. And pprof is actually efficient enough to be able to be run in production. So I don't recommend doing profiling in production, but if you had to for like just a short period of time, it's actually not the end of the world with pprof, which is really great. So just to check we have it all up and running, we go to the browser and we see the output. And so now that we have the profiler switched on, we need to generate the load to the metrics endpoint. So yeah, we don't want to do it in production, we're just going to do it locally. So we're not going to refresh the page manually like crazy just to hit the endpoints. We're going to use Go work. And the way to run it is pretty simple. We just specify -n, which is the number of requests you want it to make. So we do 15,000 in this case because we want it to run for as long as we're going to do the profiling. And so we need to turn on the profiling at the same time as we're generating the load. And that's the last line here. So we do go tool pprof, and we're going to profile for 5 seconds, and you hit the /debug pprof profile endpoint to do that. So we basically just kick off both of them at the same time. And as a side note, also with Go work, it actually gives you some pretty nice output for load testing. So if you're doing load testing, not necessarily optimizing performance, it can give you like a nice breakdown of what the responses were and what the average times were and all of that. So that's just a side note, and that's why I like this tool quite a lot. So let's go to the pprof screen again. And so the window on the left is where before we run the load generation. And then the window on the right is afterwards. So immediately we see there is something going on with the heap because it just exploded. So let's have a look at the heap allocations. So we click on that link, and the output is absolutely massive. So you kind of scroll up and down, and while we were scrolling up and down, we noticed a lot of blocks like this. And they all had this add locator time function, which was one of the functions that we basically called whenever we received when the reverse proxy was working. It was poking an external API called locator, and then recording the time it took to get the response back from that API. So that's basically what the call was doing. It's just recording the time. And then there was all this stuff at the top above it, like this new EWMA function, which came from the Go metrics package, which was an external library that we used for the metrics. It's one of the very, very popular ones to use in Go. And then, again, as a side note, the heap page actually shows you all the memory stuff at the bottom, and this is something I always forget about because you have to scroll all the way to the bottom to see that. But that is quite neat sometimes and quite handy. And so that sort of gave us an idea that something might be up with the add locator time function and the metrics library. But it's kind of yuck. Like, it's not the most human-friendly and most readable format in the world. So we kind of wanted to have a different way to view the data in a slightly more digestible way. And then, the other way to do it is to use the to basically get the profiling, the heap data, and save it in a profile file, and then we can open that, like load that into pprof, and then it just goes into an interactive mode when you can start exploring and start sort of playing around with the data a bit more. So we go from raw data to actually being able to play around with it in pprof itself. So running those two commands, and we get this. So you can run things like top 10, which will give you like the top 10 most commonly running functions at the point of taking the profiling sample. So personally, I prefer this because I find the profiling, the data loaded into a pprof a bit more readable, and then you can sort it by like the cumulative values, so you can kind of start making a bit more sense out of it. So yeah, we see the same suspects, the same metrics library, and the add locator time. And notice how this output also points us directly at where this is, so you can actually go and look at the source code if you wanted to. So we kind of got what we wanted here. So we got pointed a specific function in a specific file, which seems to be stuck on the heap. So we've got something to work with. And now that we have a suggestion to add the now that we know that, we can actually zoom into that add locator time function itself. And we can write some benchmarks for it. So that will just execute that part of code, and it will get rid of all the noise in the heap and the pprof data, which is just like system calls and all of that stuff. So here's the code. Like, the top one is the function, and it's actually really simple. It's just a one-liner. It just calls metrics, get or register the metric. So basically get the metric or register it if it's not there. And then you just update it with the time that we've recorded. And so this is the benchmark. It's pretty simple. So we just execute that function b.n times until we get some meaningful results back. And we get the following results. So we get 14 allocations for like a one line of functions. So it seems like a lot. So we then did what every developer would do in this case, and we just did a quick Google. So we just literally went go arcrowly, which was the library metrics, name of the function. And yeah, it looks like we might not be the only ones who run into this issue. So, and the GitHub issue mentioned a lot of very like low-level internal stuff of how the library was implementing the timer metric. And so we just basically went, okay, let's just go to the Go doc and start looking at the source code. And so we went to the docs, and we just happened to note, like, scroll down to the timer type, and just happened to notice this function, which is get or register timer, which is not just get or register. So there seems to be a dedicated function for the timer. So we thought, well, let's just try and swap it and see if it makes a difference. And yeah, sure enough, we're down to like 4 allocations. So yeah, boom, we kind of solved the problem. And then rerunning the profiler, we get nothing out of the metrics library in the top 10 output. So I'm not really going to explain what was wrong with that function, with that metrics library, because that's kind of outside of the scope. But the point here is that we got what we wanted out of the profiling. And we were able to also prove, using the benchmarking and the profiling, that we've actually indeed solved the problem. Like, this is our proof. So this was the case of fixing a memory leak, which it's kind of just one of the cases where profiling tools might come in handy. Before we move on, I wanted to mention something that I actually found out about yesterday when I was talking to I think Chris and Tim at the speakers at the social. So we were just chatting about how to work out what's going on with your Go routines when your program gets stuck, like in a live log or a deadlock. And they just told me about this trick. So if you kill your app with kill -6, it will emit the abort signal, but it will actually print out the Go routines profile to standard out. And I was like, I didn't know about this. Like, not something that you find in the docs. So obviously I went back to my hotel room and I had to try it. And yeah, I never heard of that trick before, but indeed, you get pretty much the same output as you'd get with your like pprof endpoints, but it's kind of a bit nicer. Like it's got a bit more human readable English words. And it actually gives you even like the state of the registers at the end. So I thought that was kind of a neat trick to mention, like especially if you're looking into finding out, like if your program is stuck and you want to know what the Go routines are up to or that kind of thing. So yeah, I thought I'll share that because I didn't know about it. So back to the talk. What about the most common case where we just want to see if there's anything we can optimize in our program? So let's take the metrics endpoint as an example again. And let's just assume we fixed the memory leak already. So we can start with something called a call graph. And basically, if you load your profiling data into pprof, you can run web instead of top 10, and it will basically give you this. And it's kind of full of system calls and some malloc gc calls. So I don't really find it that useful. I mean, it is useful, but it's not very easy to read for humans. So you have to dig through this to spot any familiar names that might be your functions from your code and not just the system calls or low-level stuff. So depending on how good your low-level knowledge is, then you might recognize some of the calls, like malloc gc is the garbage collection running. So this might suggest that maybe we're doing quite a bit of like, so malloc gc is the square in the middle. And it might suggest that maybe we're doing some heap allocations, or a lot of them. And so you can follow the arrows leading to that box to see if there are any familiar names. And sure enough, that if we do that, if we zoom in, then the square at the top, there's this function called EscapeHost, which is one of our functions. So maybe we should zoom into that part of code and see what that is up to. So this time we're not focusing so much on the memory leak, we're just focusing on general performance. So we're just curious to see what's going on in that function. So we see some strings replace, like calls to strings replace right after that. So that would suggest that maybe we're doing some string manipulations, or maybe there's something crazy string work, who knows. So I usually like to then switch from profiling the request to just profiling the benchmarks, because we want to isolate the code that we want to look into from all the background noise, all the system calls, any like HTTP calls and that kind of thing. So let's write some benchmarks for this function. This is the EscapeHost function. It's actually just 3 lines. And all it does is it takes a host as a string and it just escapes it. So it replaces dots with hyphens, and then it just gets rid of the HTTP or HTTPS at the beginning and then just returns that. And this is basically used to construct the metric name. And this is to do with Graphite, because if the metric name has dots in it, then Graphite splits it into directories or whatever. So for that reason, which is not really important here, we just needed to escape it before we call the metric name. And so here's the benchmark for it. It's very long because it's got all the cases that we wanted to test, like all the different combinations for the possible host names that we might want to get into the system. But the actual benchmark function is just the red box at the top. So again, for bn times, we just run the EscapeHost function. And then before we start optimizing, we should, and that's something that, again, I used to forget quite a lot, always take the benchmark, the sort of baseline results, as your point of reference. So before we do any optimization, we just run the benchmarks, and we save the data in a baseline.txt file. So yeah, so that we have something to compare to once we've done some work. And so we can use the Go test tool, but we can pass in the CPU profile and mem profile flags into it, and that will basically mean that it will save the CPU and memory profiling data into 2 files, CPU prof or mem prof, or however you want to call them. So we run that, and it outputs those files, the CPU prof and the memprof, and then we can load those files into pprof to enter the interactive mode, and then we can get the same kind of graph again, only without all the background noise. So it's still not that much clearer. I mean, sure, it's like it seems to tell us that these things seem to be taking quite a lot of time, and it shows you the nice hot path. But maybe we can view the profiling data in a different way, which basically will make it a bit easier to understand what's going on. Which brings me to Flamegrass, which is my new favorite thing. So they have been invented by Brendan Gregg, and there is a talk by him. It's like a pretty long talk, but he goes into great detail of how they came about to be and how they work exactly. So I put a link here. If you want to check it out, I really recommend it. They can be quite confusing to start with, but let me try and explain them using this trivial example. So this graph shows the summary of my days and the things that I tend to spend time on in my day. So. And this is actually an example stolen from the talk as well. So it's not actually my day, but go with it. So we have things like, so my day is the bar at the bottom, and it's 100% of the graph, of the width of the graph. And then we have things like process emails and hacking and dinner on top of it. And so these are the things that I tend to do every day. So they end up being visible on the graph. And then when I process emails, I tend to either bugfix or verify issues or just do something else that isn't shown on the graph. And same with hacking. Like about 50% of the time I might do testing, but the 50% of the time I just do hacking, like nothing else. And the same with dinner. And so the way you interpret this graph is this. So the width of the bar has nothing to do with time at all. So the x-axis is not time at all, which is confusing thing number one. And you can read this graph from top to bottom or bottom to top. And both directions give you some information. So if you read this graph from bottom to top, then it tells you that I spend about, 40% of my day processing emails and maybe about 35% hacking. And then the rest of it is dinner. And then if you look at processing emails, then we know like percentage-wise what part of the processing email is the bug fixing and the verify issues, and is it a big part of the processing emails or small? So like cooking, for example, is like seems to be half of the part of dinner. And then if you read it from top to bottom, it shows you the last things that were recorded when the profiling sample was taken. So basically, if you just go through the graph from left to right and read the top, like the top bars, it basically just tells you all the things that I do in my day. So be processing emails, bug fixing, verifying issues, hacking, testing, dinner, and cooking. So just reading it from left to right. So that was kind of a silly example. This is just a random example flame graph for an actual bit of code. And if you imagine how profiling data looks like, it's basically just a whole bunch of traces or paths. And some of these paths will start at the same point, but then maybe half the time you go from function A to B, but maybe half the time you go from function A to C. So if you kind of think about it, it's almost like a tree that just starts with the trunk and then sort of branches off, and then the leaves, and just ends with the leaves at the end. So flame graphs is just a great way to aggregate like sometimes hundreds of almost identical profiling traces, and basically just aggregate them and show you like the common bits and where they split up. So the top blocks as well, they show you what's on CPU. So it's sort of the terminology here is on CPU, and that means that when the profiling the sort of snapshot was taken, that's the top bit was the function that was being executed at that time. So how do you get yourself one of those graphs? Luckily, there is a really good library from Uber called GoTorch that basically does the job for you. So the first step is to get it, and then you can use it in two ways. So you can either feed it the profiling files, or you can actually profile for a given amount of time, so like 5 seconds or something, the pprof profile endpoint, and both will give you the same result. And it basically just saves a torch.svg file, so you just open that. And so this is our graph for the EscapeHost function. And the really cool thing about those graphs is that in the browser, they're interactive. So you can actually click on them and zoom in and zoom out and search for them, which is really cool. So the escape function is somewhere in there. So let's just, like in there. So let's just zoom in on that. And we can see that strings replaced is present quite a lot from the call to EscapeHost. So it actually ends up taking like probably about 80% or even more of the time. And if we hover over some other things, like the bit above, like the string slice to byte to string, it tells us that 44% of the time is spent in, 44% of the stack traces were found to be going through that path. So maybe let's see if we can optimize that somehow. So since this graph mentioned the slice, so the byte to string conversion, I thought, well, maybe let's just play around with the types. So let's try and maybe swap strings for bytes and see if it makes any difference. So we basically just did a very simple replacement of, instead of doing strings replace, just do bytes replace. And let's see if it, and just to see if it makes any difference. And, well, it kind of made things worse somehow. So, a little bit worse. So let's just start again. So, when looking at the function, we can see that the strings replace function is called 3 times, but actually the last 2 calls are there to remove the HTTP or HTTP prefix. So we can kind of safely assume that it will be on the left. So I just thought, well, how about we maybe use, instead of strings replace, we just use the trim prefix function and see if that's any faster. And that seems to have improved things quite a bit. Like we get this gigantic output because it's all the weird cases, but there is a test case called Weird8, which is the 4th one from the bottom, and actually seems to have minus 20% or minus 20% of difference on the allocations and the memory usage. So we've kind of improved things a little bit, but let's keep going. So let's regenerate the flame graphs. The top one is the new graph. And so the replace function is now only present, it went from 82% to now only under 27%. So we're definitely spending less time now in the strings replace function, which is kind of what we'd expect, because we now just make 1 call to it rather than 3. So then the other things that pop up on this graph, other than the replace functions, is the slice byte to string and string to byte slice calls. So there seems to be still quite a lot of type conversion going on. So maybe let's try and work out if we can do anything about those conversions next. So looking at the code, there's only one place where we do byte to string, and that was at the return escaped. And then I thought, well, do we actually need to return a string? Maybe we can just skip that conversion entirely and just return a byte slice. Do we need to actually convert it back to a string? And sure enough, where this function is used, it actually is only used in calls to sprintf, which can take a byte slice, and it's actually a little bit faster with that. So it turns out we don't actually need to return a string. We can just return a byte slice. So yeah, hey presto, just removing that last conversion, we got a bit better results. In the worst case, I think it's now at minus 50% compared to what it was originally, which is pretty good. And we also get 2 allocations in all the cases, and previously we had sometimes even up to 4 allocations, and it was a lot more varied. And now the new flame graph, if we regenerate that doesn't show the byte to string conversion at all. So that is good. And then I had an idea, oh, maybe I'll be clever and I'll try and return the last call rather than just saving it into that escaped variable again and returning that. But I wasn't actually sure if it was going to make any difference. I was like, well, maybe the compiler is just clever enough to do that for me anyway. And yeah, sure enough, I just got zeros everywhere and I did that. So I was like, okay, so that doesn't make any difference. That's probably just the compiler doing its job. So at that point, I was pretty much out of ideas for what else to optimize here. And the allocations we get reported is just the converting of the strings into bytes to do our work. So there's not much we can do about it. And then if we wanted to confirm that we don't do any unnecessary allocations or any heap allocations, we can do that by running the Go build with the GC flags enabled, and that actually gives you a printout and the escape analysis of all the variables. So we can see from here that nothing other than the input and the output params escape to the heap, which is pretty good. So I think we can just conclude that, well, when it comes to this function, we've kind of done as much as we can. So I hope that this was kind of useful to see a little demo. And obviously this was a simplified still. compared to like the real world problems, but hopefully it'll seem a little bit less scary now, and you can see how rewarding it can be to improve your performance by 50% or something. So just a short summary. Prioritize what to focus on, look at gains versus effort, and basically optimize the most important things first. Don't worry about the edge cases, and don't try and optimize prematurely as well. There's usually more than one way to optimize, so choose what makes most sense for you. And don't be afraid to customize your solutions and break the rules if it works for you and if you can justify it. And always be mindful about the trade-offs that you're making in terms of code readability or maintainability as you're going to optimize things. Use data to prove anything you do. So measure all the things, obviously with minimal impact on performance in production, but basically don't optimize if the data shows you that there is no need to. And remember that it's always an iterative process. So it's not enough to do it once. Usually you need to know the trends over time, and like we did with the little EscapeHost function, you kind of just need to experiment and see where it takes you. So obviously having monitoring and alerting in place, it lets you prevent like performance degradation in the future. You can even do fancy things like overlaying your graphs, your memory graphs, for example, with like deployment points, so you know exactly how your code deploys have affected performance. And above all, like sometimes focusing on the little functions and the little code changes, like sure enough, they will give you some gains, but sometimes it is the big design changes that you might need to make. And so in our case, we actually looked at all the metrics that we were outputting, and we just got rid of half of them because we were like, well, we're not actually using them, so we don't need them. And then a few days later, we actually thought, well, why don't we just make a separate health endpoint that just returns an OK, not OK, and then just not bother returning all the metrics if that's what the ops people want. So that needed us to sort of take a step back and forget about the low-level stuff for a minute, and go back to the design phase and kind of go, is this actually the best way to do it, or can we just do something else? So that's it for me. Thank you very much for listening. Not sure if we have any questions, time for questions or comments, but if we don't, then I'll be around, or you can just tweet at me. I'll be happy to chat.
Thank you, Kat. That was awesome.